engineering in 1998. He joined as an assistant professor in electrical engineering department at SGSIT Indore in March 2004 and become associate professor in 2017. He was a postdoctoral research fellow, and he completed his postdoctoral fellow from Canada during 2015 and 16. Dr. Sharma has 2 Indian patents in his credit. He has published 30 papers in Journal of International Repute, including IEEE Transactions and IET Journal. He has also published and presented more than 70 research papers in various national and international conferences. Presently, he is supervising 8 PhD candidates. His main research interest in the field of control of standalone renewable energy sources, solar water pumping system, grid-tied rooftop solar photovoltaic system, application of smart load for grid stabilization under his penetrations of distributed energy resources. Also, his work in power quality improvement and control of special machine drives. Now, Dr. Sharma is a senior member of IEEE, associate member of Institution of Engineering India, and life member of IRSS. So, now I take permission from Dr. Sharma sir to start the session. Over to Dr. Sharma sir.
Thank you, Professor. It is my proud privilege to be event, and thank you the organizers for inviting me for this talk. Yeah, actually I am going to share you as per the theme of this faculty development program, that mostly we are talking about the digital control of renewable energy systems. So the theme of today's talk is based on control aspect of the photovoltaic supply systems. Some of my students is working for a couple of years in this area, and we have government funded projects in this area. So I will try to share some of our work which we have done in last on this topic. So I will try to put my slides.
Yes, sir. Sharing. You can share, sir. No problem.
Yeah. Okay. The slide is visible? No?
No, sir. Yet. Now.
Okay, fine.
Yes, sir. Visible, sir.
Okay. So the topic of today's discussion is digital control of converters for solar power driven supply systems. We'll try to cover some of the aspects of this renewable energy supply systems on this. So these are the contents of today's presentations. We'll discuss about some of the overview of renewable energy sources, then what classification of the solar power supply system is there. Especially we call photovoltaic supply systems. Then we classify two broad categories like single phase supply system and three phase supply systems. And in this two categories, we have grid connected systems and standalone systems. Finally, we will try to check out what are the conclusion of this presentation. So, friends, if you look the scenario of energy around the world, then the demand is continuously increasing. And this is one of the fact. And the other fact is that our conventional sources of energy is continuously depleting. So there are so many regions of this regions to go away from this conventional energy sources. Some of the regions is that these sources are continuously falling, storage is falling, then efficiency of this systems is poor, and other thing is that you have to do a lot of transportation, and then a lot of space is required, and one of the main component while we are using this fossil fuel based generating stations, then there are a lot of environmental issues are also there. So in almost last 2 to 3 decades, the research community and the world is trying to go away from this fossil fuel-based systems and adopt the new trends of the energy which are based on the renewable energy. Renewable energy sources are naturally available from the source, and it does not create any pollution in the environment. That is the main important reason of using these sources. And the other important thing is that in nature they are freely available. So by that time you need not require to pay anything to use these sources. Mostly if we talk about this renewable energy sources, then mostly we have 2-3 categories on which we are relying, or which we are exploring too much. One kind of energy is through the photovoltaic panels, another kind of energy is through the wind. So, and the third one is a hydro system. So hydro is I'm able to audible?
Sir, please do full screen, sir.
Okay, it is not full. Okay, yeah, sure. Yeah. So now it is okay?
Yes, sir. Yes, sir.
Yeah. Yes. Okay, fine. Thank you. So from last many years, we are using this kind of system which we call hydro system, and we have bulky hydro system. Hydro plants are with we have plenty of power generation through this hydro system also. But now we are trying to extract the energy which are available in the some places where you have some flow of steam, and then in this area you don't have the electricity. Like if you go into the North Valley areas, there are many locations where you will find a natural flow of the steam, so you can install a small generating station there. Another important issue why we are talking about this small hydro, because these areas are quite challenging in terms of transmitting the power to them. So if there is some means of local generation of energy, then these areas can be electrified. And the other thing is that there is a constant flow of water stream is there. So you will have a constant power generation. So it is possible to electrify the area located in the close vicinity, and you can sacrifice the losses or the cost of the transmission and distribution lines there. Now the focus of the today's presentation is on photovoltaic supply systems. So we'll talk this, but while we are talking about renewable energy system, first we will have some discussion on that. So this important points already we discussed that there is a continuous depletion of conventional sources. Renewable energy sources are pollution free. That is the one of the important aspect. These are abundant in nature. Governments are encouraging a lot to adopt this sources for power generation. And if you talk today's, then you can say reasonably this technology is mature. We are trying to extract something more from this mature technology. That is a different thing. So this is also a basic slide which says that with the fossil fuels, we have a critical situations of global warming, which is significantly affecting our health, environment, and creates a climate issues. So we are focusing on this renewable energy sources. These are obtained from the natural sources, and the main sources are solar, wind, tides, geothermal, heat, water. And this energy cannot be exhausted and can be constantly removed, and as a source of which can substitute our fossil fuels. Yeah. So we are talking about this solar panels mostly nowadays. And why this solar panel? Because solar energy is abundantly available, and there are many places in our country. Our government of India and the state governments are quietly encouraging, and they have promoted and they have launched policies to install at in a distributed fashion, not in a concentrated fashion like your conventional systems are located at centric locations and then you distribute the supply. But now we are talking about the distributed generations, means even if you are at your rooftop, you feel that space, then you can install the solar photovoltaic systems and then you can start generating your own energy. The energy which you can utilize, otherwise you feed it to your nearby customer through the grid line. So these are some facts about this solar energy, that the amount of solar radiation striking on Earth's surface is about 10,000 times higher than the present global electricity demand. And to receive this solar energy, although there are many other variants of how we can utilize this energy, but photovoltaic cell is one of the very good way to harness the potential of the solar energy. Here your PV cells convert the irradiations of the sunlight directly coming into the form of electricity, which you can extract directly without any further conversion of stages. Like if you talk about your thermal station, then you have to burn the fuels and then you have to produce the steam, and then you, with the help of a steam, you run your turbine, and with the help of turbine you run a generator, and then you produce the electricity. But this is a single stage conversion, right way from the your solar, the radiations irradiate, you can directly have the conversions into the form of electricity. But we know that when something comes in a very good way, then there are certain challenges also. So that's why because of these challenges, we are not very much. Even today, we are trying to improve the technology. We are trying to give more mature technology for its applications. What are the main issue with this technology? Because when they are freely available, that is not in your hand. When the radiation is available, you have to convert this energy. When there is no radiation, then you have to sacrifice that there is no radiation. But as far as the load is concerned, you cannot in a straightforward way, you cannot guide your loads that, okay, when the radiation is available, you utilize the energy. When radiation is not available, you don't utilize energy. In a straightforward way, you cannot say like to your customers. See, in the night time, we need the illumination, but in night time, unfortunately, we don't have the solar. So we have to identify certain applications where how we can meet the demand with the generation. That is one of the important issue. An issue is that there are certain situations like if you look at this radiations from your solar energy, even in the daytime, you will find the intermittency in the generation. When the cloud is there, the radiation will fall. So definitely the generation will also fall. When there is no cloud, you have an ample of generation. But you cannot directly control your load that you exactly follow the pattern of the clouds. That's not possible. That's why the technology is required in between that, which can satisfy the need of your customers, as well as which can satisfy the demand of the generation. So the basic idea here is that you have to work with the intermittency of the generation, and the other thing is that you have to work for the in a very basic way. Although there we have to restrict the optimum power generation from the supply system also. But right now we are not in a position that we need to restrict the generation from our supply system, because we are very much hungry. We need the active demand of the power at any moment of time. So that is the reason we are talking about the optimum energy extraction. If the radiation is full, then how you can operate your photovoltaic system that you have the maximum power extraction from it. This is the situation of our Indian grid that is on, these are the current year data, 2020, from the standard government side like MNRE. Presently, we have the capacities installed into the grid system is around, from the renewable energy sources, it is around 87 gigawatt. Out of this 87 gigawatt, most of the portion is covered through wind, solar, and some portion is covered through small hydro, and then we are also talking about biomass systems, which are basically the substitutes of your diesel generation. Now, this is the current situation, and the government for 2022 targeting, presently we are at 87 gigawatt, and government is targeting to reach this number up to 175 gigawatt by the end of 2022. Out of this, we are targeting solar to a very high number. So you can see there, the contribution of solar is going around 57.14% out of this complete production. And the second number is from the wind. So wind is also coming in a big way. But presently, the more focus of the government is to enhance the solar systems in a wide manner. Now, that was the situation for the Indian grid. Now, if you look at some of the situation where you are talking about you are away from the grid. So, yes, it is possible that in the classification we have seen that these systems can be classified either in the grid connected mode or in the off-grid mode or standalone mode. Yes. According to the MNRE, some of the data are available where we are utilizing these sources of energy, renewable energy, for the off-grid applications where the grid is not accessible actually. So from this, if you look at the solar PV supply system, it is around 0.9 gigawatt. Biomass gasifiers are around 0.16 gigawatt. And waste to energy is around 0.18 gigawatt. So this total comes around in the off-grid is around 1.265 gigawatt. And some small portions for other kind of renewable energy system is also there, and which the micro hydro is coming in a big way for the northern area of the country. Now, if you look at the historical development of the systems, then initially in 2000, around 12 or 13, the government is targeting for 20 gigawatt, and it is targeting for near about 2022. But very soon the government has reshuffled its target, because the generation has reached up to 100 gigawatt in 2015 only. Out of this, 40 gigawatt is only from the solar rooftop, and it is in 40 gigawatt we are targeting for 2022 with the economy of US dollar 100 billion. India expected its solar generation capacity 8 times from 2.6 gigawatt on 2014 to 20 gigawatt as on January 2018. The country, if you look at the pictures year-wise, 3 gigawatt has been added in 15-16, then 5 gigawatt has been added in 16-17, 10 gigawatt is added in 17-18. So these are the facts till today. In 2020 also up to 2019-20 also we added around 8 gigawatt. And with the addition of this, you will notice that because the price of solar energy is very less, so because of the mature technology, the prices are continuously going to fall. So today we are talking about this solar photovoltaic energy, and these are some of the advantages we have seen in the previous slide. Applications of this photovoltaic supply system. Now we will talk about the photovoltaic supply systems. So there are two broad categories. One category, you simply say that you are feeding all this energy to your grid supply system, and whatever the ancillaries or utilities the consumers connected with your grid will have the rights to use this energy. If you look at the standard, there are of using this energy which are not directly connected with the grid. Okay, one of the main advantages you will receive that your distribution cost is reduced to a large extent. So some of the applications, maybe at a small scale or maybe at large scale, application like might be you aware that nowadays we are talking about solar-based LED lightings. So are you have seen and at the crossing point of the road that traffic signals are illuminated through the energy. So that is one of the important applications where you at the utility point you install a small based on smaller panel. Solar panel will convert the light energy into electrical energy. You use some storage system also there. You store this energy in daytime and then you utilize this energy when it is required. So that is one very important applications of solar energy where your distribution line, you are going to completely and eliminate the other maintenance required of this line. So the cost is going to reduce. That is one application. Another application is pumping. Might be in the yesterday lecture, this water pumping applications that nowadays farmers are this solar-based water pumping systems in our country, and there are many indigenous industries started its production in our country, which is based on because the main challenge of the farmer is that they need electricity and they need pumping for their crops. They need water for their crops when there is a huge or active shortage of the electricity. That time they need, like the festivals are coming. Sometimes it happens that during the festival time, the farmer also need electricity and the urban area also need the huge amount of electricity. So they have to sacrifice, and maybe it was experienced in the past because of the need of the water. Many of the crops have not grown as it is required. So that was a big challenge for the farmers. So presently government is putting a lot of subsidies in this sector. So they are promoting the farmers to install the solar photovoltaic based water pumps for the irrigation purpose. There are many other applications of this water pumping also, like you talk about the your community water supply where you need the electricity, or might be you are not aware, but we are in Indore, and we are lifting the Narmada River from near about 80, 60, 70 to 80 kilometers away from Indore, and the head is also there. So you need a large size of the pump there. So just these pumps are already installed, and we are continuously receiving the water from this Narmada River. But the main challenge there is that in this lifting process, you need a lot of electricity, and it creates an additional burden on your grid supply systems. So there is a scheme where we are exploring an opportunity that how we can install independent solar system there, which can be utilized for lifting the water. It will be a huge reduction in the demand of the electricity on the grid supply systems. Another prominent application is for electric vehicle. Okay. Nowadays, we are talking there is a big boom on this sector, and there is a huge scope for the electrical engineer, power electronics engineer in this sector. Okay. Now, these electric vehicles are coming in a big way, right? We are observing that your cars are coming with hybrid cars are coming, electric cars has started to come, and major sector where we are using electric vehicles are in terms of auto rickshaws, your city buses. We already started. Okay. Now, when this vehicles have been started, then the another issue is that how you charge them, because you have to provide a facility to charge them. Like if I am a professor, I am visiting from my place, and if I am using a electric vehicle, then I have only a two job, that I have to rush to my institute and then I come back to the institute. So because why I start at 9 o'clock, I will come back at 6 o'clock. So I will have the need of parking station at my institute also, and I need a parking facilities or the charging facilities at my home also. So while my vehicle is at the institute, if the charging facility is available there, and because it's a daytime, you have the solar, the parking station can be in terms of solar based system. So that will be a very good idea, and a lot of peoples and lot of companies started working in this area. Okay, that is another prominent application is in case of communication tower. We know that these towers of your mobile companies are located here and there, and they are distributed. Maybe there are some locations where they are in the isolated areas where there is no feasibility of grid. So we have a solar supply system there, and the electricity need is very small for this communication tower, but they need any electricity. So the supply system may be based on photovoltaic supply. Another important area where the solar supply systems can provide great support. Another prominent application which is coming in picture is refrigeration and air conditioning. You know that here the win-win situation is that your load demands fall. You need a lot of cooling requirement during the daytime. You need a very small cooling requirement during the night time. So let's say that the generation and load follows each other. So that is another prominent application. We have big size cold storage to protect our crops, to protect our vegetables, to protect our foods. So that can be driven through the solar based supply systems. Storage also there, or you need the facility of grid connected also there. It may, if it is permissible at that location, but if the solar supply systems are installed there, it provides a great relaxation to your grid supply. Another application for the cold areas where the heating is the one of the major requirements for power consumption. So heating will consume a lot of power. So like the countries like US, Canada, need a lot of heating requirements during the winter season. So that can be also catered to this solar-based supply systems. Now, what is the solar supply system which we are talking about? So this photographs will give you just a broad idea about this. So just see this picture which has been taken from the net. It looks to be attractive, so we have taken. So this is your radiations which is coming on solar array or solar panel, and from this solar panel you are converting this energy with the help of some converter. A power electron converter is required between solar panel and your storage. Now you are filling this from the solar panel to your storage system. So it's a battery bank. Okay. Now the battery, the nature of the power which is available at the battery bank is DC in nature. Photovoltaic supply system also provide the DC. So this power which is available in DC, there may be some loads at your residence which supply, like LED bulbs, CF, maybe some. Now, if you talk about the advancement in the technology, your ceiling fans are also special machine drivers. So they can also be supplied through directly from the DC supply at the DC bus of the inverter, because all the special machines are driven through and kind of converter which we call voltage source converter. So such kind of demands means your ceiling fan requirement or your refrigeration requirement, because the people started trying the special machines in the refrigeration systems also, freezers which we used in our houses. Convert this DC power with the help of a DC to AC converter called inverter. System to TVs, ceiling, table fan, ceiling fan, and the other appliances which are running with the AC supply. Okay. So the direct power light energy is converted into, so it's a direct conversion, one-to-one mapping. The form of electrical energy is converted to the desired manner with the help of power converters. So now you talk about this power converter. This may be a DC to DC converter, or it may be a DC to AC converter. So this converter performs some objectives, control objectives, which we are going to discuss in this session. Now, this typical characteristic of the photovoltaic supply system is very important. If we are able to understand this supply system characteristics, then it will provide quite flexibility in understanding the complete operation of the systems. So the VI characteristic of the PV panel. So if you look at the x-axis, the PV voltage is there. If you look at the y-axis, PV current is there. And in between these two, you have a graph. And this graph is at a particular irradiance, solar irradiance. So usually we consider that maximum irradiance in our country is reaching up to 1 kilowatt per meter square. So that is maximum irradiance. So we'll get such kind of characteristics between voltage of the solar panel and the current of the solar panel at different irradiance. Now you will notice origin says that at this point voltage is 0. Panel voltage is 0, but the current is maximum. So that point is known as short circuit current capability of your panel. Okay. Another point is this one or this one. The current output from your PV panel is 0, but the voltage is maximum. That is known as open circuit voltage of your PV panel. I hope you understand the difference between the PV cell, PV array, PV panel. Okay. So at mass, we talk about PV panel, that these PV panels are available from the different manufacturers, and these are available in the different ratings which are coming to us. So one PV panel, the standard size may be 250 watt or 300 watt or 400 watts. These panels are available to you. Now this single stage panel, you have to connect in series or parallel depending upon the voltage requirement at the panel side or the current requirement at the panel side. So you may connect these panels either in series or parallel. And the same philosophy has been observed while you create the array from cell to array or from array to panel. So the same strategy is adopted to create this. So I am here. So now if you look at this point, there is no current. If you look at this point, there is no voltage. So we know that how we get the power. The power is basically the power output from electrical system is the product of, if it is a DC system, then it is a product of voltage and current. You will get maximum power when you have a reasonable amount of voltage available through the panel with the reasonable amount of current available, current drawn from the panel. So if you start plotting the power characteristic with this PI characteristic of the PV panel, then you will get such kind of shape. How you get such kind of shape? At each discrete point, you need to multiply the voltage available at this point and the current available at this point. So if we go to a discrete multiplication of voltage and current at the different point, you will find such characteristics. Now, if you look at this characteristics, you will find this. In this characteristic, you want the power from your panel. You don't want either a single quantity, like either it is a current or it is a voltage. You want the product of these two. Then only this power can be available to your grid or it can be available to your other applications. So if you multiply this two quantity, you will notice at a typical value of voltage of PV panel and at a typical value of current of PV panel, which is obviously not the value of short circuit current and not the value of open circuit voltage, you will get a maximum power. So the basic idea of operating your PV panel is to extract the maximum power. So you need to guide with the help of a power converter, which is coming after your PV panel. Okay, which is coming after your PV panel to operate this PV panel at such a point where you will get the maximum power. So that is the job of algorithm, which we call maximum power point tracking algorithm. That is the job of an algorithm, which we call maximum power point tracking algorithm. Got it? Now, this voltage and this current, both are the functions of the irradiations on your panel. How much irradiations the panel is receiving, based on this irradiation, you will get the respective characteristics. So that's why if you look at this characteristic, you will have the different characteristics at the different irradiation profiles. Here it is 1 kilowatt per meter square. Here it is 0.8 kilowatt per meter square. Here it is 0.5 kilowatt per meter square, and so on. So you have a discrete characteristic. Just for the understanding, we have this characteristics, but radiation may be in between this. So you have a enormous number of characteristics from the maximum radiation to minimum radiation. Now, for each characteristic, this point will shift. Now, at 1 kilowatt, this is the max point at which you are advised to operate. While you talk about this point, you are advised to operate at this point. While you are at this characteristic, you are advised to operate at this point. So this characteristics moves like this. Yeah, you can see 1 kilowatt, 0.8 kilowatt, 0.5 kilowatt, 0.2 kilowatt. So for the different radiation profile, you have a different operating voltages and different operating currents, where your system, control system, guide you to operate at this point. So your control system should be sufficiently intelligent to grab that, okay, radiation is changed. Now I need to change the operating point. That is the requirement. at this point, because right now we are talking about very simple things, but I request the participant, the moment you find any discussion, please stop me at this point. We can start the discussion. We try to solve your queries. The objective of this presentation is not to show you too many slides, but if I am able to show you only a few slides, but with a better understanding, which help you to start your research work, or which help you to grab the better understanding of this area, that will be fine for me. Now looks at the various types of solar PV supply system. The other way is also advised by your organizer of this event, that you can, whatever your question, you can put on the chat box and then they will ask it there. So, okay, this is a broad classification of your solar photovoltaic supply system. Broadly, we classify in two categories. Either you are interested in feeding to the single phase grid, or you are interested in feeding to the three phase grid. Based on this, your subsystem may be a grid connected system, or it may be a standalone system. A standalone system may also be possible that you have a single phase load only. So you are interested to feed the power to single phase load only. Or it may be a three phase. So there are two categories, standalone and grid connected, in both versions, single phase and three phase. Now again, further if you go in these categories, now you have the broadly two kinds of topologies which we used. One topology we call single stage conversion topologies. Other topologies we call double stage conversion topologies. In single stage conversion topologies, again you have a classification. Either you have a isolated topologies, or you may have a non-isolated topologies. In isolated categories, in the single stage, broadly we have two sections. Either we are talking about flyback topologies, or we are talking about interleaved flyback topologies for the inverters. In non-isolated topologies in the single stage, either we call double grounded topologies, or we call common grounded topologies. So these isolated topologies can further be classified. There are numerous classifications of this. Okay, each topology will advise you some better performance in terms of certain variable, certain control variables. Other topology will provide you some better performance in terms of some other point of interest. So if you classify these topologies, this is just a small classification. Some more classification may be possible. It is based on our best of the literature exploring. So isolated boost half bridge converter, it may be a dual boost converter, it may be a current fade push pull converter, it may be a hybrid resonance DC-DC converter, it may be a DC-DC boost converter, it may be push pull converter, it may be your full bridge converter may also be possible there. Okay, some Zeta converter is also possible there. Some Leo converter is also possible there. So you may have a numerous classification for this. Similarly, you can have the classification under the non-isolated categories, where isolated means somehow you are going to introduce the transformer between your PV panel and the grid interface. Non-isolated means there is no scope of transformer in between these two topologies. Or even if you are introducing the transformer, that is just at the output end of your converter. Now, if you talk about, so this is the classification for grid connected. Similar classification is also possible in three-phase version for this. Although the difference in single phase and three-phase version is that while you are talking about three-phase version, means you are talking about the power which is greater than 5 kilowatt. In single phase version, you are talking about the conversion which is less than 5 kilowatt or equals to 5 kilowatt. That is the only difference. Now, if you look at the standalone version of this system, in standalone version, there are two possibilities. Either you are developing your system with in the support of some energy storage system, or you are developing your system without the support of any energy storage systems. So two ways are possible. Now here you have all the applications which we have seen in the previous slide: lighting, water pumping, then refrigeration and air conditioning. Okay. all these applications will come under this categories. Now with energy storage, again you have two possibilities, whether it is a single stage or double stage. And without energy storage also you have two possibilities. It may be a single stage and double stage. But without energy storage, the basic idea is that you are trying to control your load in such a way that that it tries to follow the source demand, source generation. Okay, so you have a lot of sacrification in the nature of the load what you are controlling. So this is a broad classification. Now, in some of the variation, you will find that storage systems are also used with grid connected mode also. Now, we have discussed that Government of India has planned a scheme, and that is already in practice for the farmers to install the solar water pumping system, which are based on solar panels. Now, government has moving a step ahead behind this. They want to provide the incentives to farmers that because they have installed a solar panel, and the rating of solar panel, like if you have connected a 1 HP pump, then the rating of solar panel may be near about 900 watt or 1 kilowatt. So if you are installing this solar panel in the farmer's lane, and farmer is not supposed to utilize the solar panel around the 365 days. He needs the pumping only when he needs the irrigation needs. Otherwise, this is in standing conditions. So what the government has learned, they have launched a scheme that you connect this solar photovoltaic panel with the grid supply. Where at the point, if the grid supply is available, you connect these systems with the grid supply also, and they are calling that it is not a consumer only. The farmer is not a consumer, but it is a seller also. When he is not using the electricity, because it's anyhow solar panels are installed there, so he start selling this energy to the grid supply system. So now the flexibility is widened. Now previously the panel rating depends on the water pump rating, but now panel can be of bigger size based on the space available with the farmer, or based on the how much investment he can afford. So that is a new concept which is coming in picture. Come to the next slide. Yeah. So this is just a way of presenting that panel is there, converter is there. Now this converter may be a single stage converter. If it is a single stage converter, then you are talking about DC to AC converter. All the control responsibilities are now with this DC to AC converters. If it is a double stage conversion, then you have two converters here. One converter you are calling DC to DC converter, and another DC link is there. So your solar panel is connected at this end. Then another DC link is there, and this DC to AC converter can be connected with your grid supply, or can be feeding to your stream. Or you may have a topology with a galvanic isolation, isolated topologies. So in isolated topologies, such kind of version is there. So initially you have a DC to AC converters, because the transformer is there. For the working of the transformer, you have to use the topologies which work efficiently with the transformer action. And then again, you have the AC to AC conversion after this state. Many are possible here. You cannot say that you can stick on the single variation. So this two classification we have already discussed. Either you are a grid connected mode, or you are in standalone mode when the grid is not available. Now this is a very basic and first topology which we have explored here. In this work, we have targeted for the small customers. Like you are targeting a slum area residency, where the area available for the rooftop is very small. Maybe 100 square feet area is available, where a small family is residing, and this shade is available there. So you can install a 1 kilowatt panel, or you can install a 600 watt panel there, because their electricity need is not very high. So here this system is developed for the single phase version, and the power rating of the panel is near about 600 watt or 650 watt. So the panel rating is 650 watt only. Based on this panel rating, the PV voltage is near about 174 volt, and rated PV current is near about 4.5 ampere. So the basic idea with this development is that you installed a solar panel at the rooftop of a customer, which is having a very small area, and then you try to cater its electricity needs. So what is the demand behind 100 square feet area? It's very, either he need one or two lighting systems, he need one fan, he need a small systems for the other cooking requirements or something else. That is the requirement. So it is basically based on this targets. Now the big challenges in the development of this kind of system is that because the solar panel is operating at a low voltage and your grid supply is near, because it's a 230 volt supply. So grid supply is 230 volts. And the panel voltage is less, near about 160, 170 volt. So for the effective working of this single phase VSI, actually you need to lift the voltage. You need to lift the voltage at least a value which is equals to the peak of the supply voltage. So if it is a 230 volt, then you need to lift the DC link voltage for the effective working of this converter to up to minimum 325. Then only this converter will work effectively. This is one challenge. Another challenge is that because the system rating is very small, so you cannot sacrifice too much with the conversion efficiency of the system. So what we have done here, we have used a DC to DC converter with a minimum number of elements. So it's basically a boost converter, PV panel, followed by a boost converter, followed by the DC link, followed by a single phase full phase inverter, followed by a small filter element, and then it is interfaced with the grid, which is coming to this slum area locality house. Now we work on this systems. So recently we got a publication on this work that was published in IEEE Transaction in Industry Application. So here there are two control objectives. First objective is to operate this PV panel at the maximum power point, and the other objective is to have the control of this inverter, and the control of this inverter with the grid disturbances also. So first we'll talk about boost converter control. Now for any maximum power point tracking algorithm, there are a lot of conventional approaches available in the literature. So first we develop the system with the conventional approach like perturb, observe, incremental conductance, and then we try to explore some more refined algorithm which will provide a better results. So while we develop this fuzzy logic control based maximum power point tracking algorithm, we find that there is an improvement in the conversion efficiency around 3 to 4%. So what are the inputs to this fuzzy logic controller, which is used for the MPPT controller, and the output of this FLC is provided to provide the switching to this first converter switch, this switch SDC. So here there are two inputs required. First is known as EK, which we call error, and the second one is the gradient of this error, difference of this error, the difference of this error. So EK and del EK are obtained with the help of this expression. PK is the power obtained at the kth sample. Pk minus 1 is the power obtained at k minus 1 sample. Vk is the voltage monitor at the PV panel at case sample. Vk minus 1 is the voltage observed at the PV panel at K minus 1 sample. And daily K is the difference of this error at K sample and K minus 1 sample. So how we are measuring this power? By measuring this panel voltage and measuring this PV current. Now these two inputs are given to this control. So this is actually the complete control scheme used for the fuzzy logic control for maximum power point tracking approach. So here you can notice there are two variables which we are sensing: PV voltage, PV current. The product of these two is obtained, and then the product is P power, and the one sample is hold to get the difference in the power, and this 2 is divided by the error in voltage. So that is your E, which we have obtained the previous expression. The second one is this error and the difference of this error with the previous sample. So this is error and this is the difference of error present at the previous sample. So that is daily. These two inputs are fed to the FLC block. Now this is a Mamdani control where this FLC, with the help of this Mamdani control, this FLC is developed. 3 membership functions are used for each input. So one variable is input variable daily, other is your input variables delta E, and this is your output variables. So sorry, 6 membership functions are used here. 1, 2, 3, 4, 5. Sorry, 5 membership functions are used for each variable. One we call negative big, negative small, 0, positive small, positive big, and same is for the others. Now then this FLC will provide you the output with the usual procedure which we use for the fuzzy logics. So you can notice here the output of this FLC is the small deviation in the duty cycle at kth interval. Then this is added with the duty cycle which you are getting at the output previous duty cycle. So this is added here, and this output, this is compared with the sawtooth signal to generate the gating signals for the constant frequency operation. Now here you look at the control which we adopted for the inverter or the VSC, voltage source converter. So here we developed a 5th order generalized integrator based control, and objective of this control is to, first objective is to go for the synchronization with the grid supply. That is important. Even you installed if you connect a new generator with your grid supply system, then you have to follow a standard procedure for synchronizing your generator with the grid supply. So that is also you have to adopt with your this inverter while you are switching on your inverter. So the synchronizing signal is required. Now the synchronizing signal can be obtained in a very straightforward. Actually, you need the template of the voltage, grid voltage. So the template of grid voltage can be obtained in a very easy manner, because you need the unit template which is in phase with your grid voltage. That unit template can be obtained by dividing the running value of your voltage signals with respect to the amplitude of your voltage signal. That will also to provide a stable control for the operation of your system, because the grid voltage had lot of disturbances. Sometimes the grid voltage will have the harmonics, sometimes the grid voltage will experience a shake, sometimes the grid voltage will experience a swell. So you should have a robust kind of control which can be sustained till the standard guidelines allows you that your photovoltaic supply system should be grid supply. Till that point, your control should not lose its control capabilities. So here, what we have done, we have used a generalized integrator-based control, which we call fifth order generalized integrated controller. So this is one loop. So here we are sensing the point of common coupling voltage, the voltage of your grid supply, we are sensing. And if you look at this loop, this is the fundamental loop, where the output you will get is the alpha component of your supply voltage and the beta component of your supply voltage, V alpha, V beta. And these two are basically for the third harmonic and fifth harmonic. What we consider here in this implementation, we consider that because the predominant harmonics which are present in the supply, maybe third harmonic, maybe fifth harmonic. So if you separate these two harmonics from the fundamental supply for getting the synchronizing signal, then there are good chances that your controller will remain stable. So these three loops are created with the help of this generalized integrator, which is quite common, frequently we use. The transfer function, the detailed transfer function of this generalized controller may be available in the next slide, or you may refer this paper which is available in the future publication. Here you will get a fundamental, and then these three subtractors are here for this fundamental loop. Basically, the idea is to get a pure fundamental, even the harmonics present in the load supply voltage. So we are subtracting the components of this third harmonics, if it is present in the supply voltage, fifth harmonic if it is present in the supply voltage, to obtain this component. Now, if you look at this figure A, in this block, this complete scheme is developed. So you will get alpha component of the voltage and beta component of the voltage. The square of this alpha component and beta component and the root of this component will provide you the amplitude of the voltage. Now the amplitude, this alpha component is in phase with the supply voltage. Beta component is lagging 90 degree with your supply voltage. So actually we need the alpha component, in phase component, because we are considering that our inverter is operating at a unity power factor. It is not injecting any reactive power to the grid. It is only supplying the reactive power. So this template is obtained with the help of this procedure, and you are having some reference value of your DC link voltage. Actually, this scheme is keeping the DC link voltage up to a value of 180 volts. So we are comparing the reference with the difference value, and the error in the voltage is actually sensed, so that you have an indicator that what amount of power is coming to the DC link from the PV panel. Your objective is simply to transfer this power to the grid supply. Whatever the amount of power through the MPPT algorithm coming to the DC link of your voltage source converter, the same amount of power you need to transfer to the grid. So with this objective, this controller is working. So this error, the difference in the voltage error at the DC link is processed through a PI controller, proportional integral controller. The output of PI controller we are calling the reference current, amplitude of the reference current at the grid side, and the other component is subtracted from this reference component just to reduce the tuning burden on this PI controller. What is this component? Actually, this is the component which is gathering from the PV panel measured parameters. So what we are doing, the product of PV power is divided by the amplitude of grid voltage, and then it is multiplied with the gain of 2. So that this component we are calling feed forward component. Feed forward component. This component is subtracted from the reference current, which is obtained from the DC voltage control loop. So that this is your grid current. Actually, what is the job of component? Actually, the job of this component, actually, what amount of current you want to transfer to your grid, keeping in consideration the losses of your converter systems. Keeping in consideration the losses of your converter systems. So actually, this is the component. If you assume that you have a lossless converter system initially, if you assume that you have a lossless converter system, then the amount of power which is received from your PV panel is to be supplied to the grid. That is the main objective of. And the difference component which is creating because of the losses taking place in your switching operation of the different switches which we are using in your converter, like a step-up converter and your VSI, that should be compensated by the PI. Otherwise, if your system is lossless, then we can straightforward omit this section. But in practice, it is not a lossless system. That's why it is required to come. So the difference of these two components, we are the grid current difference. This grid current difference is compared again with the sense grid current. Okay, control is on grid current. You have to shape the grid current. You have to shape the grid current. You have to shape the grid current in such a way that it operates at unity power factor, so that there is no further reactive burden, especially for this scheme. It is not universal truth that you don't want the VSC to supply the reactive power. In some next control schemes, we will discuss that, yes, we operate the VSI to feed the reactive power to the grid also, but under different situations. Right now, we are considering that the injection to the grid at unity power factor. Unity power factor means you are feeding the power to the grid, means it is exactly 180 degree to your phase component of the voltage. So these two currents, sense and the reference current, are compared, and then again it is processed through a proportional controller. Usually it is a proportional controller. Okay, and then you need to release the switching signals for your full bridge VSI. So unipolar control scheme is used. I hope you are aware about this unipolar control scheme which is used. So this control variable, the output of your PI controller, which is your modulating signal, is given to upper block, and its inverted signal is provided to with a negative sign to the lower block. The upper block will provide the getting signals for switch S1 and S2 and of one leg, and this block will provide the getting signals for the other two switches. I hope up to this point there is no doubt to the participants. Here this control scheme. So basically this is your carrier signal. So you are comparing the carrier signal with the modulating signals. So this is your modulating signals. So this is one modulating signal, here the another modulating signals. So these two are compared in the real time with this carrier signal, and based on this you will have the voltage at the terminal of your VSI. Yeah, just look at the performance of this scheme. These are the simulated result. Later on we will see the experimental result also. So this single slide will provide you all kind of variants which are taking place in your system. Let's try to understand this variables plotted here. So the first variable, able to read these signals. So I will read down the signals. This is the irradiation which is applied to your panel. This is the PV panel voltage. This is the PV panel current. The third one is PV panel current. The fourth one is the DC link voltage at the DC link voltage at the input of your VSI. this is the supply voltage waveform. So looks to be a sine wave. And this is the current which is fed to your grid, which is exactly 180 degree out of this supply voltage because you are feeding this power to the grid. The next one is the load current component, which is connected in the model. The next one is the power, load power. Actually, there are three graphs shown here. One is the PV power, other one is the grid power, and the third one is the load power. I'll try to explain each one. So this is your load power, this is your generated power, and this is your grid power. The second one is grid power which is fed to the grid. Because in the model we have also considered that some load is also connected at the point of common. And these three are the spectrum of Fourier analysis for supply voltage, supply current, and load current. Now just try to focus on the transients which are created here. Okay, so one transient is created at near about 0.5 second. One transient is created near about 0.5 second. Another transient is created near about 0.8 second. Okay, and another transient is created near about 0.9 second. The first two transients are related with the disturbance, extreme disturbances in your radiation conditions. Extreme disturbances in your radiation, which we have called the intermittency in the generation. Okay, so by the 0.5 second, the solar irradiance are close to its rated value. At 0.5 second, the solar irradiation has suddenly dropped to a very low value, close to 500 watt per meter square. It's a sudden intermittent variation. Then 0.9 second, the irradiations are suddenly jumps from 500 watt per meter square to 1000 watt per meter square. Okay, and at 0.9 second, by 0.9 second, there is no load connected at the load bus. So all the power which you are receiving from the solar photovoltaic panel is going to the grid. You are injecting all the power to the grid because there is no load connected at the point of common coupling. But at 0.9 second, you have switched a highly nonlinear load. You have switched a highly nonlinear load, right? So we'll try to understand this pattern. So the moment irradiation falls from 1000 watt per meter square to 500 watt per meter square, you will find this version is little bit zoom here. This point is little bit zoom here. So at this intermittent point, you will notice there is a sudden disturbance in the PV voltage. Because your MPPT algorithm is working, it requires some finite time to settle down. Till that point, it is noticed that the PV voltage has little bit jump in its voltage. And at the same point, you will notice that the PV current has also fallen to also settled to a new value corresponding to the MPPT point because the radiation has fallen. So obviously the power delivered from your PV panel should fall. So current has shifted to a new value with a little disturbance. Now before that point, the DC, if you notice the DC link voltage, a very small disturbances in the DC link voltage at the input of your VSI is noticed. It is near about 180 volt. Okay, and a small disturbance is noticed here. Hardly any disturbance is noticed here. You can see. Okay, it is maintained at this value. Only what you notice here, the ripples are high and here the ripple is low. Can anyone guess why these ripples are coming on this single phase at the DC link of single phase inverter? Sorry. Yeah. I'll tell you, then you explore your points. These ripples are generated because your supply frequency is 50 hertz. So 2 times of the ripple is developed at the DC link because of the switching of your converter. Frequency which is and the voltage which is available at the DC link capacitor is around 100 hertz. So the signals are oscillating at 100 hertz. This phenomena is quite obvious in case of single phase system. At the DC link you have the oscillating ripple voltage is there, which is double of the supply frequency. Okay. Now you come to the grid voltage, because grid is considered to be steep grid. So hardly any disturbance in the grid magnitude, grid voltage magnitude is noticed. So it is perfectly sine wave formed. But you can notice the change in the, at 0.5 second, you can notice the change in the magnitude of grid current. Why it is so? Because the generation is reduced, so the power you are injecting into the grid is also reduced. Okay. Now comes to the load current. Load current is 0 at this point, so there is no load current. Then you will find the load voltage. Yeah, sorry, this is generation voltage. So this is generated voltage. This is generated voltage. So generated voltage, if you notice, the generated voltage is fallen. Earlier it is close to 600 watt. Now it is fallen corresponding to the new value, because radiation has fallen. So it is close to around 250 watt or 260 watt. And there is no change in the load because load is 0. But you notice the change in the generation. Earlier generation is high. It is shown with the negative value, because as per the convention, you present the generation. If you are receiving the power from grid, it is positive. If you are feeding the power to the grid, it should be negative. So here the power is negative, presented with the negative value. And because the generation is fallen, so this grid injected power is also fallen. And the condition remains stable till a next disturbance comes in picture. So next disturbance comes in picture at this point. When next disturbance comes, you will notice the vice versa changes. PV current is increased, DC voltage is stable, but its ripple magnitude is changed. Grid current magnitude is also changed, and generation power is also changed. PV panel power is changed. Grid power is also changed. Okay, and the next disturbance you will notice, now there is no disturbance from the source side, the disturbance from load side is noticed, but because your controller is working properly, it is perfectly synchronized, no disturbance is noticed. Now the grid is, the load is start at this point, 0.9 second, so we'll notice a reduction in the grid injected power. So the grid injected power is now the generated power minus load power is equals to the grid injected power. If the grid load power is greater than the generated power, then you are supposed to receive the power from the grid. So that's all about this results. You can notice the TSDs of grid current and the grid voltage are within the acceptable limit of IEEE 519. Now, because you talked while you develop your control algorithm that your control is stable, even the disturbances are introduced in the grid supply. Like there is a dip in the voltage, there is a fall in the voltage, there is a harmonic in the voltage, there is a sag in the voltage, there is a swell in the voltage, there is a DC offset in the voltage. Whether your synchronizing signal is stable or not, that is presented in this results. So we will try to focus only on the grid voltage. So this is your grid voltage. Now this is your nominal value of the grid voltage. Here the swell is present in the grid voltage. So grid voltage is little bit high than its nominal value. The sag is there. Grid voltage is less than its nominal value. And the DC offset is present. When DC offset is present, the waveform will be shifted to the side where the offset is present. Now, if you look at the template of voltage, even in all these disturbances, so what you will notice, the template, synchronizing template, is perfectly constant in magnitude and steady in its cycle. All such disturbances are created, even the DC offset is present. It proves that your control remains stable even all the disturbances comes in picture to the grid voltage. In this case, again we are looking to our synchronizing signal, because that is the important signal at which your complete operation of your PV panel system depends, which is interface with the grid. Now here, if you notice again the supply voltage, you are introducing the frequency variation here. You are introducing the third harmonics in the supply voltage. You are introducing the fifth harmonic in the supply voltage. You are introducing third and fifth both voltage in this case. But you will notice your synchronizing signal is not even affected by a small value with such a heavy disturbances in the supply voltage. It proves that your control system or the system will remain in perfectly synchronizing. This is the picture of the prototype developed in our laboratory at SGSITE. So you can notice this Launchpad TMS 320F28379D is used for the development of algorithm. And here it is inverter section. The DC to DC converter is developed here, which we are calling boost converter. And this is the your variac through which your complete supply system is connected to the grid. And these are the interfacing inductors and filters which are developed. And this is a part of the load which is connected as a non-linear load. So these are the results, hardware results. So this is the power fed to your grid at some typical radiation. This is the TSD of voltage. This is the TSD of current at this power, which is very small. And this is this proves the efficacy of the MPPT algorithm at this radiation. So you can notice the operating point is just at the knee. Your operating point is quite close to the maximum power point. It proves that the efficiency of maximum power point taking algorithm is close to 99.38%. Now, this is another version where we are working. This is a high gain DC to DC converter. Now, the main challenge, because as you are reducing the panel rating, then the PV panel voltage is also going to reduce. And we are targeting to a customer, to those who cannot afford a very big panel or who don't have the space of to occupy these panels, and which can be, even if the actually this is a part of the a project which has been given by the government of state government of Madhya Pradesh, MPCST, Madhya Pradesh Council of Science and Technology. They given us a responsibility to develop a cost-effective solution for establishing this technology for the slum areas. So we are trying to explore some topologies which can be cost-effective. So government will provide some subsidies, and whose indigenous production can be started in the nearby industries. So we are in this work also we explored, we are targeting the topology for the small rating panels. So the panel rating is close to 300 watt, 255 watt is given here. With this panel rating, the operating voltage, PV voltage is 50 volt only, and the PV current is 4.5 ampere. And we have keep the DC link voltage close to 350 volt in this case. And obviously the grid voltage in our country is 230 volts. So again, the challenges are to lift the low voltage PV panel voltage to a high value with minimum losses in this process. What we have done that if there are two customers which are close to the vicinity and two panels which are located at a space, so it is possible to develop the converter for the individual panel of near about 250 watt or 300 watt, and to connect these individual panels to the common DC bus. So here it is shown for the two topologies only. But suppose you have two customers which are quite close, and if it is possible that you install a common system for all these converters, all these panels, so you can save the cost of conversion from DC to AC. So here in this topology, we are lifting the voltage from 50 volt to 350 volts. So two switches are required in this topology with certain around some more passive elements are required. But what we have done for reducing the losses of this converter, we are working with a very high frequency. Near about 40 kilohertz we are operating with switching of these converters, so that the sizes of these elements are very less. So its static losses are reduced. And here, in place of MOSFET, ICTE, we are using MOSFETs here, so that the switching frequency can be high. And with the help of a proper snubber circuit design, we have tried to reduce the switching losses also here. So we can sacrifice with a high number of components here. So two such panels are connected. The output of these two panels through these two different converters are coming to a DC link. And then this DC link is feeding to an inverter, and then we are feeding to it. The basic idea of using the different converters which are located, because the rooftop are even adjacent, but their MPPT point may be different. So it may not be a good idea to use a single DC to DC converter and operate it with a common MPPT algorithm, because the irradiation may be here different than the irradiation which is available here, because they have a situated at a distance which is little apart, and it may possible that you may connect some more number of converters. So only you have to take care of the design of this, and then the wiring can be distributed, because it's you are talking about maybe a space of a length of 100 feet or 200 feet, so may not be too much distribution losses taking place here. So these are the different operating modes of these converters. I think we are running short of time now. So just it is showing that the converters are operating with the different modes. So in first mode, these two switches are on, switch 1 and switch 2. So this inductor is stored energy, and this inductor also stored energy. So the supply side. So this is your mode 1. Mode 1 means switches are on. These two switches are on. So current is flowing like this. Current is flowing like this. And at the output section, current is flowing like this. So this white lines are showing the path of the current during the mode of operation. When these two switches are on, off, then the path will be like this. The current will flow like this. Current will flow like this. Current will flow like this. So actually, your CUC converter or SEPIC converters, there are different sections where we are taking the energy storage, and then this storage is dumping to the output capacitor. So these are the output capacitor basically. So the idea here is to minimize the ripple in the PV current. The idea here to lift the voltage from a very small value to a high value, because lifting the voltage from 50 volt to 350 volt is not possible with the help of a boost converter, simple boost converter. Here you need a high gain boost converter. This is the another mode where the path will be following like this. You will these diodes will conduct. Now this capacitor, this capacitor, and this capacitor will deliver the energy to the output capacitor. So in this way, this converter operates. The similar algorithm is used for MPPT extraction. The only difference is that you apply these algorithms individually for each high gain boost converter. The same algorithm is adopted here, and the fuzzy logic rules are given here, which was missing in the previous slide. So how you have distributed your membership functions for the different values, that is presented here. Now here we try a little bit more with this algorithm for the synchronization of voltage, and we have a little bit changes in the final algorithms for getting the reference generator current. So here we have added the load component also. So to have the more stability in the control, this load components are also added. So you are sensing the load current, and then you are extracting its direct and quadrature-axis components for the synchronous reference frame, alpha beta to DQ frames, and then here the remaining part of this algorithm is identical what we have explored there. Here the unit vector and its angle is estimated with a little bit different approach what we have discussed in the previous sections. Here you are sensing the PCC voltage, and then you are getting the alpha and beta components from the difference in the value of these components, alpha and beta component. You are integrating these components. Then you are this is omega, which for our grid is considered to be constant, and then you are getting the synchronizing signals omega t, and from this alpha beta component you are getting the templates which is required for synchronizing the your inverter, single phase inverter. The only difference here is that because again we are operating at the unity power factor, the converter is operated at unity power factor. So unity power factor for the grid current means the reactive component of the load current is also supplied by the converter. The reactive component for the operation of inverter is also supplied by the converter. Reactive component demand of the filters which you are using for filtering the grid current is also supplied by this converter, so that you can keep your grid current at a constant unity power factor. So this is the blown of the same thing. Your hysteresis control is applied here. Only the previous scheme, unipolar PWM scheme is applied, but here we are hysteresis control. These are the results for the DC to DC converters. So you can notice this is the radiation. Here the radiation is constant, it is not changed. In the first case, radiation is constant, it is not changed. So this is PV voltage, this is PV current, and this is the power generated by individual panel. And this is your second, this is the operation at the grid side. So this is the radiation, and this is the PV voltage, and this is the grid current which is inducted under the change in the radiation. So radiation is changed here. So that is going to be recognized here. So you will notice the fall in the currents. This is the power. If you change the radiation, the PV panel voltage will also deviate from its value. PV current is also deviates from its value, but it always ensure the fuzzy logic control always ensure that the power is corresponding to the maximum operating point when the radiation falls. This is the DC link voltage, almost stable, and here you will notice in this case you will notice you can notice the DC link to near about 400 volt. Here the load current is changed. So here you are applying the load current for some this small interval of time, and then it is zero. So while the load current is change the load power is changed, and there is a change in the grid power. This prototype development has been observed in the laboratory. So this is your high gain boost converter, which you have seen in the figure. And these are the results of this high gain boost converter. This is the PV current. This is the PV voltage. This is the DC link voltage, quite close to 350 volt. And this is the PV current. And this is the voltage across first switch. This is the inductor 2 current. This is inductor 1 current, quite smooth. This is inductor 3rd current. So many passive elements are there. This is the DC current at the output of your VSI capacitor. This is the DC voltage, and this is the PV current under this situation. Then that work was published, previous work was published in PESA conference, which was held in Kerala last year, this year only, 2020, January 2020. And this work is published in the conference UCon, which has been recently happened in New Delhi. Sorry, this is the work published in IEEE IS conference of 2020. So again, we tried another high gain boost converter with some variation in the topology. So again, you are talking about to lift the, this is 555 watt panels, because we have a target to develop this skills for the different ratings. But again, you have to lift from 105 volt to 400 volts so that your VSC operate effectively. So this is another converter. I'm not going to discuss too much about this converters right now. Here, the inverter section is identical, what we have developed. But the difference in the previous topology of high gain converter in this topology that here the active switch is only one. In the previous topology, there are two active switches are required. So cost wise, this version is more effective than the previous version. And we are getting the identical lifting in the voltage. These are the version of this high gain boost converter with single switch. The switch is off here, so the power is flowing through this path. This is off version and this is off version. When switch is off state, the power is flowing like this. And when switch is on, your power will flow like this. That time diode will circulate the path for the output current. So these two capacitors. Again, fuzzy logic is used for, the sliding mode control is used for the maximum power extraction. So for sliding mode control, you will notice that again the sensing variables are both are same. PV voltage and PV current is sensed. And from this PV voltage and PV current, you obtain the small change in the duty cycle. Small change in the duty cycle. This is the transfer function of your voltage for your high gain boost to boost converter. So from these expressions, you can observe that this transfer function of high gain boost converter is little bit gain is little bit high than the gain you received from your boost converter. The boost converter you have VPV over 1 minus D, but in this converter you have a gain up to plus D over 1 minus D VPV. So you will receive a comparatively high gain with this converter. So you are sensing the DC link voltage, you are sensing the PV voltage, you are sensing the DC link voltage, and based on this you define what should be the nominal duty cycle of your converter. So this nominal cycle is obtained, and from your algorithm the difference in the duty cycle is noticed. The main advantage what you gain with obtaining the nominal duty cycle is that while you start your converter will never operate in an unstable region during the starting also. You need not require to control your converter, because from the beginning you are starting with some more stable value. So you will not notice a abrupt change in the D with this approach. And sliding mode control is obtained as usual what we use for the other. So this is your sliding surface. So D over DIP, differentiation of PV voltage with respect to current. So then if you modify this, you will get PV steady value, constant value, plus del VPV by del IP, and you define this delta D is some constant K sigmoid of psi, which is sliding surface. And then you modify this your modified duty cycle corresponding to this sliding surface, you will get like this. So you will always operate in the sliding surface. Not much disturbance in the nominal value of the duty cycle is required. Even it is not required in the other converter also, because there is not much change in the PV panel voltage. Even the radiation is changed slightly, hardly only 5 to 10 volt in the DC PV panel voltage is noticed to be changed even in the normal operating conditions. This is the algorithm used for the extraction of the synchronizing component, which is quite similar to the previous algorithm which we explored in the previous case. Only the difference in the case of high gain converter. This is the transfer function of the high gain converter, and the Bode plot is obtained to prove the stability of this converter. So you can notice the Bode plot is compared with the previous converter, previous synchronizing techniques which were reported in the literature. So you can notice this is the technique which is reported in this proposed work, which is published in the IS 2020 general meeting. So we call modified second order generalized indicator. And the previous techniques which are reported are FOGI, fifth order generalized indicator, and SOGI, second order generalized indicator. So the comparison of stability is presented here with the help of a Bode plot of the transfer function of this converter, which is obtained from the developed model. So this is the transfer function. If you got the Bode plot, and if you see the transfer function of this this model, you can notice it is there is no overshoot noticed even at the cutoff frequency also, while you will find notches at the different frequencies with the different component, and its response is also fluid from DC value to greater than the cutoff frequency. So it means this developed high gain boost converter operates effectively under wide disturbances in the PV panel voltage and current conditions. It proves that. These are the results. These are the switching signals for the DC converter switch. This is the inductor 1 current, this is inductor 2 current, and this is the switch voltage of DC converter switch. This is the switch current, because switch is opening and closing according to the frequency. The operating frequency is close to 30 kilohertz. And these are the voltages at the different elements of this high gain DC-DC converter. Diode 1 voltage, diode 2 voltage, diode 3 voltage, diode 4 voltage. And these are the results obtained under sag and swell conditions at the supply voltage. So you can notice the templates. So template is in this, and this is omega t, the plot of omega t. under the changes. These are the alpha and beta components of the templates, and these are the results under the change in the solar irradiance conditions. So radiance has changed, so you notice the change in the current. This is the DC link voltage, this is the grid voltage, and this is the grid current and load current. Due to the change in irradiance, grid current and load current changes, and these are the powers under different cases. And these are the results under constant irradiance. Actually, as per the regulations, you can present the results with disturbance in one variable, not the disturbance in all variables. So here the irradiance is constant, but change in the notice our load current is changed. So when load current is changed, the change in the there is no change in the PV power. PV power is split, only the changes in the grid power and the load power is noticed. This is the linear load connected at the grid. And this is the performance comparison of this high gain boost converter with the conventional boost converter. Okay. Now you in the research you have to justify your work that your development is working better than the existing development. So here these are the switching signals. So this blue lines, blue results are presenting the proposed high gain DC converter results, and red line is proposing the conventional boost converters. So these are the signals for the boost converter and high gain boost converters. And this is the current. Now you can notice the current ripple in inductor. The current ripple in the supply PV panel side inductor is high as compared to ripple in the high gain boost converter inductor. So it is almost flat. It is close to a constant value. So means there are good chances of achieving the MPPT in a better way as compared to the boost converter. For the similarity, we have keep the same algorithm for both the converters. That's why you notice in all these three topologies, we are keeping the same algorithm for both the converters. These are the switching voltage stresses. Switching voltage stresses are a little bit high in conventional boost converter as compared to high gain boost converter. The current magnitude, if you notice, in your boost converter is less. In conventional boost converter is less as compared to high gain boost converter. Then this is the DC current. So the ripple in the high gain boost converter is less in case of high gain boost converter in the ripple in current. And these are the diode voltages. So diode voltage stresses are comparatively very high as compared to high gain boost converter. Another topology reported, this is isolated topology. So push-pull kind of configuration is used. So this converter will provide the galvanic isolation between your grid and the PV panel, because there are chances that leakage current start flowing. If isolation is not there, then leakage current start flowing between your PV panel and your grid supplier, switching converter and PV panel. So if you provide the galvanic isolation, then certainly you can eliminate this leakage current. So this is a push-pull configuration which is used for this implementation. So you are converting with the help of, you are switching the push-pull converter for obtaining the MPPT. So maximum power extraction is obtained with the switching of these two converters, and this VSC is controlled in a usual manner. This work is published in GUCOM, recently held in New Delhi in October 2020. So here the panel rating is little bit high, 1 kilowatt. So the panel voltage goes up to 125 volt, and the DC link voltage capped at 400 volt. grid voltage is 490. So these are the different modes of operation of this isolated push-pull converter. So this push-pull converter serves two purposes. Because the transformer is introduced, it has to lift the voltage. It has to change the level of voltages between this. So this transformer is operating. One switch is on. So switch is on. So current is flowing like this, and switch is on. Current is flowing through this converter. So this is a boost kind of configuration with the push-pull topology. So here no switch is on, the two switches are off. So current is circulating following this path. Current is circulating following this path. And when you close the switch, energy is stored in L2. And when you open the switch, this energy is circulating like this. And vice versa operation taking place with the other switch. So if there are two switches, then certainly the rating of these two switches are reduced, because each switch is supposed to be active in the hop cycle corresponding to the switching period. Again, the same algorithm is employed here, fuzzy logic, and this is a VSI control. So in this technique, we have little bit modification in the conventional second order generalized integrator. So this equation is modified here. So we have implemented a simplified version of second order generalized integrator. So these are the results with eigen push-pull converter. Switch 1 voltage, switch 2 voltage, currents. You can notice here the differences. And these are the transient conditions. So transients are taking place at this point, transients are taking at this point. So you can notice the changes in the PV power. Load power is constant. Changes in the load generated power. These are the disturbances in loads. It's a single phase load, so you can either increase the magnitude of load, you can remove the load, or you can decrease the magnitude of load. That's all you can do here. Now, just a little bit, I would like to touch standalone topology with the three-phase systems. So here, just consider that the energy is available at the DC link. We are adopting similar kind of strategies what we adopted for a single phase system, and then this DC link is available, which is coming. This energy is coming through our renewable energy source, and we have a three-phase inverter. And take an example that you are feeding a scanner. So the beauty of the control algorithm which is implemented here is that there is no PI controller in use. Certainly, might be you aware that if the PI controller is introduced, then in some way it will increase the complexity, because you have a botheration of tuning of this controller. And the tuning, even if you do the tuning, then tuning will work in some disturbances, tuning will work fine. In some disturbances, tuning will not work fine. So you have to go and tune your systems to give its optimum performance in each different transient cases. So here in this algorithm, all the PI controller have been eliminated. Only the mathematical expressions have been used here. So what we are sensing here, if you notice, we are sensing three load currents, we are sensing two line voltages. With the help of this two line voltage, you can estimate the three phase voltages, and then we are putting alpha beta transformation. And then because it's a standalone case, so with the standalone case, you have to decide your own reference signals. So suppose that your phase voltage are 230 volts, So you have to generate the templates of 230 volts signals with a frequency of 50 Hz, and then you are compared with the actual signals, and based on the comparison you will generate the error signal, and these error signals are again transformed into the 3-phase signals, and with the help of PWM you apply the signals to your 3-phase VSI to give your and output voltage. So this kind of approach completely eliminates the requirement of tuning signals. More detail about you can explore in this paper which was published in IEEE conference on energy system inferences proceeding AICTE. This paper is accepted for publication in renewable energy focus, but it is not published, so it is not mentioned here. More detail about this paper you will find in this conference, which is IEEE conference. So you will get the details in the IEEE Explorer about this control algorithm. This is the prototype of this algorithm we tried in the laboratory. For this we use D-space controller, which is available in the laboratory for its real-time implementation. And you get this results. So this is your supply voltage waveform. This is supply current. You can notice here, this is a line voltage, phase A current. This is same line voltage, phase Y current, phase third phase current. This is your inverter currents, I guess. Yes, this is the capacitor current, which is used in the filters. This is this current. So phase A, phase B, phase C filter current, these are the load currents. Okay. So, these are the PWM voltage at the output of the inverters, and these are your load currents. Now you can notice here the TSD of load voltage is quite less after filtering. This is around 3% only. These are the PWM voltage pattern at the terminal of your AC terminal of your VSC, but it is not at the output terminal of your grid supply, external grid. This is the power which is delivered to grid, and this is the power delivered from your VSI. This is the power delivered to the load. These are the cases with nonlinear load. So this is nonlinear currents. This is capacitor current under this condition. This is your low filter currents, inductor currents, and these are the TSD of load current. All the 3 phases. This even you are feeding your non-linear load, but the output voltage is perfectly signed. So it is good for supplying the other loads. So these are the powers at the different terminals. These are the dynamic results. So these are the 3 voltages, grid voltages, standalone grid voltages with the load current. So load is completely removed at this point, but you can hardly notice any changes in the grid voltages. So it is because even if a single PI is used with the algorithm, you will notice, because it's an instantaneous. With the help of mathematical expressions, you are deriving the reference signals. So hardly any change in the terminal voltage are noticed. Here you can notice suddenly you are applying the voltage, but no change in the terminal voltage. That is the effectiveness of the control. These results are with the dynamic loads. So here you are applying the dynamic load. By that time, the terminal voltage of your VSC is something wrong. These results are little bit obtained with a little bit compressed result because we have to show the dynamics. So at this point, the load is connected. So this is dynamic load, means you are at the VSC output of your inverter, you are starting the induction motor of near about 0.25 kilowatt rating. So the starting current of your motor is something like this. It requires some time with a DOL starter. So the current is settled after some time. But you can notice your grid, even with the dynamic load and with the standalone grid, your grid is not going to collapse. That is very important. Even a small dip in the voltage is noticed. That is obvious, but even with such a high interest current of your motor, the grid is not collapsing. That is very important. So this is three-phase current of your terminal. Only the grid voltage is noticed at this point, and it is recovered till the currents are settled to its value. Because these are the abnormal values where you are not designing your systems to observe this abnormal value, but your control allowing you with a small reduction in the voltage, your control is allowing to be settled. So your system is in the working condition. That is important. So at the end, we can conclude that yes, there are still a lot of challenges for the effective deploying this technology, and there is a need to improve the conversion efficiency of the converter, so that you can reduce the size of the panels, especially in the low power ratings. And with the help of effective control, it is possible to provide the stable control. And there are a lot of opportunities in the control segment that you can explore some new algorithms. Right now, I showed you the algorithms with a unity power factor operation of the grid, but you can notice that your inverter can be factually utilized because it is a solar inverter. You are not utilizing the optimum capacity of the solar inverter. Your inverter is free in the night time. You can explore the capability of this inverter in the night time to provide the reactive power support to your grid. Otherwise, also your inverter is partially utilized to feed the active power generated from your PV system to the grid. Partial capacity of your inverter is still unutilized, which can be used for reactive power compensation, which can be used for stabilizing your grid. So there are many issues which can be still explored, and it can be operated. Another issue which is very popular, we are also trying this issue that your systems which are located in the distributed manner, which can be able to self-sustain. That self-sustain means they can supply the load which are in the local community when the grid fails. So it will like your microgrid systems. If you install your rooftop solar panel at your rooftop, and if your grid fails, at least this rooftop system should be able to feed your house electricity requirements. That will be a good enough for the explorations. So that's all about the present lecture from my point of view. Your questions are welcome. I stop my presentation at this point. The questions are welcome.
Thank you very much, sir. Participants, any questions, any queries? Any queries from participants?
So there are two things. Either they all understand the things.
Yes.
Or they are not able to show them.
Okay, sir. Thank you very much, sir. Sir, shall we conclude?
Yes, of course. If there is no question, we can conclude.
Yes, yes, sir. Thank you, sir. Thank you, sir. Sir, okay. आहे का?
Hello.
Yes, Jitendra. Yes. Do you have any query?
Sir, yes, I wanted to know from the sir. Sir, is there any way of increasing the efficiency of the solar panel?
Yes. Presently, if you see the panel coming to the, they are claiming that it is close to 80 to 20%. Right? But there are, in the research angle, there are some new materials has been invented where the researchers are claiming that the efficiency is increased up to 24 to 25% conversion efficiency.
Okay.
Yeah. So that is one aspect in which people are working. Those who are material engineers, they are continuously working. That is one aspect to improve the efficiency. Another way to improve the conversion efficiency is to go for cogeneration. So right now the panels we are using, these panels are straightforward used for the generation of light energy to electricity energy. But during this process, these panels are also receiving the heat. So like if we have the, because if you are installing these panels at rooftop, then definitely in your house you need the need of hot waters.
Okay.
So if we can modify the structure little bit of the solar panels so that they can release the energy to the cold water. That way also you can have the bi-generation of your energy, that some part of the energy from panel you can extract in the form of heating your waters. That waters can be used in for some other application in your house, and it also helps to cool your panels. So the efficiency of your panel will also increase.
Okay. Sir,
Yeah.
can you suggest some material for which the solar panels can be made for the increasing the efficiency?
Yeah, presently silicon is widely used for this, and I believe that it is not in our it is not belongs to my area, that what kind of material is can be suggested to enhance the efficiency.
Okay.
It is a job of the material engineer.
Yeah,
Those who
material.
are exploring this area.
Yeah. Okay, sir. Thank you, sir.
Okay, thank you.
Yes, any participant have query? Any? Okay, sir.
Okay, thank you very much.
Thank you very much, sir. For
again, thanks to the organizers and the audience for passionate hearing.
Yes, yes.
And even if at the, because this slide will also be shared to you, even if at the end of this course you feel some doubts or questions are there, you can mail me or you can call me. My number is also there in the slides. Thank you very much.
Thank you very much, sir. You have accepted our